Good morning, everyone. Welcome to today's webinar on innovation in renewable and sustainable cooling. My name is Durga. I'm the project manager for Reef-UKC project and your host for today. I hope you can all hear me okay. There seems to be slight delay. Well, good morning again, everyone, and welcome to today's webinar on innovation in renewable and sustainable cooling. My name is Durga, and I'm the project manager for Reef-UKC project and your host for today. I hope you can all hear me okay. We encourage your questions, so feel free to type them into Q&A section at any time. We will address them at the end. Thank you for joining us, and let's get started. First of all, I would like to invite Dr. a.rezk from Western University, provide an introduction of the EPSRC network. Ahmad is principal investigator for Reef-UKC project. He is an academic in mechanical engineering and leads research in sustainable cooling, sustainable heating, and thermal systems. His research expertise involves enhancing the performance of the thermal systems, including material to system level development. Ahmed leads the Sustainable Process Research Group in Sustainable Development Research Center at Aston University. Over to you, Ahmed, now.
Thank you, Durga. I hope everyone can hear me okay. I'll share my slides now on the screen. Is it okay, Durga? Can you see it now? Yeah. Good morning, everyone. I just want to spend with you 5-10 minutes to introduce our network, which is Renewable Energy Access for Future Net Zero Cooling, Reef-UKC. So who we are a group actually of academics and people from industry, and we aim to work together actually to develop system level solutions for future net zero cooling. Why we do this? We are now proactive for the increasing demand for cooling actually in the UK specifically. So currently the figure for energy consumption for cooling only in the UK is around 14-15%, but there is more emerging sectors actually needs cooling more than before. Specifically data centers, quantum computing, and hydrogen sectors. This will actually increase the demand for cooling by several folds actually. And we will face a problem in the future. The problem is if we keep doing what we're doing, we most likely run or power the cooling system using grid electricity. Giving the additional load of vehicle electrification actually in the UK, I think the grid wouldn't be able to cope with this increasing need. So our approach is to get cooling off the grid to make it more renewable powered cooling. That's why we need to develop new systems and we need to power clean cooling technologies using renewable energy available in the UK. What we do in the network, we do networking activities like webinars, in-person workshops. You attend in person and participate in Reef-UKC. Our aim actually is to enable today's early career researchers to become the future leaders in this topic, right? So we don't provide solutions only now, but we need actually early career researchers to take the lead in the future to enhance this further. We provide you with some training master classes actually specialized in clean cooling technology and renewable energy technology as well. All what you need is you need to participate. There is no additional cost. We pay all the cost for transportation and all these sort of things actually, right? So your participation is free of charge. We cover all these charges actually. We funded by EPSRC to run these activities. Okay, so all what we need from you is to engage in these activities, whether it is online and or in person. Okay. Uh, We promote multidisciplinary research and we pave the way to more transdisciplinary research in the UK. And we act on 5 fronts. The first front is technology development. Because we are engineers, most of us are engineers actually, we want to develop new renewable power cooling technologies. So we look at clean cooling technologies and how to integrate it with renewable resources. We consider the environmental action or environmental impact of what we develop today for the future. We consider actually sustainable businesses and business model, and we try to fill any gaps with the current policy to accept the new solution and the new options actually, and how to make the unusual usual for the future. Uh, we don't work in silos, right? We try to engage with other ongoing activities funded by EPSRC and other funders to fill the gaps. So we don't want to repeat other people's work. We complement what other people do. We promote actually stakeholder engagement. We promote ADI in research, equality, diversity, and inclusion. We aim to generate impact. That's why we try to engage more with industry. We need to take this new solutions to the industry, and we try to promote the industry investment in research and development actually. We provide you with seed funding to enable you actually specifically early career researchers to do the preliminary investigation for bigger projects. We aim eventually to become a bigger supergen hub focus on renewable power cooling systems. So we started firstly actually with the core members group of 10 universities and some industries from cooling background, heat exchangers, and renewable energy. We have partners also from City Council, Birmingham City Council, and Belfast City Council. And we try actually to reach out more local authorities. So this where we started. Now we have increasing number of academic participation in the network from industry and from international stakeholders and partners from other universities and from other companies. And this actually only for 3 quarters because we started in July 2024, right? As we go along, we expect actually this network to grow further and further and pave the way to the SuperGen hub in the future. So funded. I mentioned earlier in the past few slides that we enable research focus on renewable power cooling, which also paved the way for SuperGen hub. We've been successful actually to fund 5 projects in the first phase, and this project actually within 4 themes. The first theme is renewable power cooling system, how to integrate cooling with waste heat and address actually thermal pollution of existing cooling systems. We looked at real-time digital twinning simulation actually in renewable energy and cooling as well. We looked at the social aspect and accessibility actually of the new systems and how to make the unusual usual for the future. And we find actually a nice intersection between these themes in 2 points. The first one is thermal network, and the second one is net zero cooling technologies. And we found actually that the social acceptability for the new technology and the social science is one of the core elements in the future multidisciplinary research in these two areas, right? So anyone attending today or anyone you know, you can tell them that they can apply for this next round of funding, right? And to be successful for next round of funding, you need to propose a project which is based on the theme of our network, which is renewable power cooling technology. Your project should be multidisciplinary. Uh, you should show us that you are planning for bigger funding because we seed fund your idea. We don't fully fund your idea, right? So we help you actually to get started with the funding, specifically if you are early career researcher. You need to show us that you work very closely with early career researcher. We also promote the early career researcher to lead the project if possible. And we promote also the partnership with industry. Any partnership with industry, whether it is cash contribution or in-kind contribution, is very welcomed, right? The most important thing that your project engaging with industry. They don't need to fund or putting cash into your project because sometimes we find a very smart SMEs as they need to grow, but they need to partnership with a university in order to get further fund and so on. So we encourage these activities, right? So if you are interested, try to tick these boxes, right? We will announce actually the funding call soon in next few weeks. It is through two stages of assessment, short application and presentation, and then you can start your project, get the money and start your project. Right. How to be part of Reef-UKC? Send us an inquiry on at this email reefukc@aston.ac.uk. Participate in our activities like this webinar and the future workshops. Follow us on LinkedIn page and follow us on the website. You will find a lot of useful information on the website, and you will see actually the smart brain that work with us in this and our partners actually in this network. They are all amazing people, smart people in their disciplines. What is next? We plan for few activities in 2025 and more will follow on. Just keep tuned and you will receive announcement actually for these activities. So the next one would be a multidisciplinary workshop at Aston University, and this is planned by the end of May, beginning of June. The final date will be released soon. We also plan to partnership with SEEP conference and we allocate 1 day symposium dedicated for our activity. So you can come around and present in this symposium. We will organize a policy-oriented workshop in London South Bank University and more will come in the future actually. So just stay tuned. Yeah, thank you so much. And I will leave it back to hand it back to Durga to yeah allow other participants actually to present to you.
Thank you, Ahmed, for a detailed introduction of the project. I would like to extend my apologies to some of the attendees for today's webinar. We had some technical glitches while admitting some of the attendees. The system kept on hanging for a few minutes, so apologies again. Moving on, I would now like to invite Dr. Moura Mevravar. Moura is an associate professor at the University of Birmingham. Moura specializes in computational mechanics and experimental modeling in geotechnical engineering, focusing on geoenergy infrastructure, including energy piles and offshore wind turbines foundations. She has significant experience using biomaterials for ground engineering and has worked on innovative solutions for renewable energy projects. Her interests include smart infrastructure, particularly developing novel sensing technologies and efficient methods for infrastructure condition assessment and sustainable design. The title of her presentation is The Role of Energy Geostructures for Heating and Cooling in UK. Over to you, Moura.
Okay, thank you. Thanks, Durga. And hello, everyone. Good morning. And thanks for inviting me to participate in this webinar. So, Durga, I don't know if I can share my screen now.
Yes, please try and I'll confirm.
All right, then. Okay, then. Can you see my screen?
Something happening. Yes, it's there now.
Then.
Thank you.
That's good then. That's good then. So, can you hear me clearly?
Yes, Moura, it's fine.
All right then. Okay then. So, as Durga mentioned, my presentation is about the role of energy geostructures for heating and cooling in the UK. And so I'm an associate professor in geotechnical engineering at the University of Birmingham. I was introduced earlier, but just mentioning again. So my presentation outline, firstly, it will be about myself briefly, my research expertise, and then I will talk about geothermal energy in general, give you a brief introduction. What is it about, in case your background is not very relevant to geothermal or geoenergy sector. I will move on further and talk about the difference between shallow and deep geothermal. And then we will go through energy geostructures and also their advantages as a renewable energy will be discussed. And I will talk about energy geostructures in the UK, their potential for the UK for both heating and cooling, and the barriers for their uptake will be discussed. And then the next part, I will talk about our facilities at Birmingham, which allows us to do lots of controlled large-scale testing on buried infrastructure, including geostructures for heating and cooling. And I will briefly mention about our current projects on energy piles, which is considered as energy geostructure to produce heating, as well as recently started to look into the project for cooling energy. So, okay, it is working. Next slide. So about me, my research focuses on two parts which are interconnected and linked, basically smart and sustainable civil infrastructure, integrating my expertise in computational mechanics as well as experimental modeling from small scale to large scale. And I specialize in geoenergy infrastructure since I started my PhD a long time ago. I have been working on energy, geoenergy and infrastructure for geoenergy, started with novel supporting structure for offshore wind turbine, and now moving on to energy geostructures, including energy piles. And also I have experience of working with novel sensing technology, focusing on fiber optic sensing technology to monitor geostructure, as well as transportation geotechnics. So key area was already touched, but emphasizing on digital twins for geoenergy systems, including energy piles, which is the current project that I'm leading. and AI application in the design, analysis, and maintenance of transportation geostructure, and in general for any types of geostructures. So are my main research areas and expertise. So let's just minimizing. Can you see the figure clearly? Because I
can see the solar figure.
Yeah, okay, clearly, because the team's details are is shown on the right-hand side on my screen. I don't know if you have this one on your screen as well.
No, it is
Yes, I can.
clear.
That's good.
Yeah, it's
That's
clear.
good then.
Yeah.
So that's good then. Okay. What is geothermal energy? So geothermal energy is all energy stored in form of heat below the ground in ground subsurface. It is very reliable source of energy and considered as a low carbon energy and renewable, which doesn't depend on weather conditions, even in the UK. It is available across the UK at different depths from few meters to kilometers, several kilometers. And so based on the depths, it can be extracted and stored using different technologies. In the figure I put on the right-hand side, you can see some of the parameters, factors affecting the flow of heat in the UK. So generally speaking, geological condition as well as hydrological condition can affect the geothermal energy efficiency of this system. So it has this energy, geothermal energy has a very low spatial footprint, and it is scalable. So it is scalable means that it can be used for both heating as well as cooling individual homes, different types of buildings, and not just individual residential homes. It can be applied and used for commercial buildings and other sorts of buildings. And also a source for district heating and cooling. And geothermal energy, I can say, is a key asset for energy security and independence from gas import, and it is significantly important for us in the UK. The UK currently uses only a small fraction of geothermal potential, and there is a considerable, huge potential to increase the UK contribution in the energy mix and take this potential and use it as one of the reliable source of renewable energy for cooling as well as heating. This has recently received better attention. Use of the underground for integrated heating and cooling and thermal storage is now becoming increasingly important. But still, compared to other EU, US countries, we are far behind them. So, next slide. Okay. There is a difference between shallow and deep jet geothermal. I'm going to very briefly touch it, and my focus today will be basically based on shallow geothermal. I'm not going to talk about deep geothermal. Shallow geothermal energy is the low-grade heat, so normally between 10 to 25 degrees of centigrade, which is stored in the shallow subsurface, and normally we consider up to 500 meters below the ground as a shallow geothermal. And it required the use of ground source heat pumps and can be used in almost everywhere in the UK for both heating and cooling of the buildings. So in the picture, right hand side again, you can see that the ground temperature variation over depth. So as we go deeper, so obviously we can have higher degree of temperature inside the ground. Deep geothermal energy is the heat stored at depth larger than 500 meter, and temperature within the ground increases with depths in line with the local geothermal gradients, which in average we consider 25 degree of centimeter per each kilometer that we go down in the UK. So that's the difference between shallow and deep geothermal. Next, I'm going to move on and further talk about the main purpose of today's presentation, which is energy geostructures. So firstly, energy geostructures are part of ground source heat pumps. So during presentation, I may talk about ground source heat pumps and geostructures both together. So it's important to know that this is a part of ground source heat pumps. There is a slightly differences, but it is categorized as a part of it. Energy geostructures are a type of shallow energy technology where building foundations, such as piles or other buried infrastructure like underground station, metro stations, tunnels, sewer pipes, and underground walls, as you can see down here in the pictures, are used to access heat from the ground. It can be used for both heating and cooling purposes, as well as so they are acting as a structural element of a building. So they are novel dual-use engineering substructure, which means that they can be used for heat transfer, storage, as well as original purpose of their design, which is structural function. The use is becoming increasingly popular in delivering cost-effective and considered as one of the sustainable options for shallow geothermal energy. They are constructed as a part of ground source heat pumps, as I mentioned earlier, system, and the market has been increased for their demand in the market, and there has been lots of interest recently in doing technical and non-technical research to make them a backbone of renewable energies, both in the UK and abroad, so mainly in the EU countries. The wider potential to integrate to district heating networks has yet to be explored and very well explored. One note to add is energy geostructures have advantages over other traditional drill boreholes, so which is kind of a part of ground source heat pumps again. The main reason is heat transfer pipes, which are embedded. You can see in this picture that we have pipes embedded inside the geostructures. For example, for energy piles, they are embedded inside the concrete pipes. So they are not in direct contact with the ground, and they are part of the structure, and so we don't need to do excavation for their implementation, which means that the capital cost for drilling, which we have in case of traditional drill boreholes, is very, very much lower and reduced. So therefore, this technology offers lower investment cost than conventional drilling boreholes. So this is one advantage which I just wanted to mention. It's not in my slide, but it's worth mentioning. So it can be used in tunnel linings. And so you can see one example in the middle, in the wall of underground parking. So huge potential if we want to use our underground spaces. So there are plenty of advantages of energy geostructures or in general ground source heat pumps. So the first one is low impact and space efficient. So this technology use minimal land area and creates low visual and noise disruption. So which makes it very ideal option for urban settings. Second one is their alignment with national infrastructure. So about more than 600 billions of pounds allocated to around 700 UK infrastructure projects recently, and many of them they need deep groundwater potential. So which means that we have huge potential of underground infrastructure investment that we can embed energy geostructures, so pipes basically inside them. You can see again examples here. So those underground infrastructure can be energy tunnels and piles for buildings and walls and base slabs. So for all, and sewer pipes, for all of them, we can embed pipes and use ground energy and use the ground energy for heating and cooling. The third one is opportunity for repurposing. This is um, uh, referring to existing infrastructure, which can be adopted for heat sourcing and seasonal thermal storage, which later on in summertime we can use them as a cooling and source for energy, energy for cooling purpose, and in winter time, so we can use the ground heat for heating the buildings, for example. Next one is cross-industry innovation. This is mainly applied to ground source heat pumps. So we can take the technologies which is very, very well established from oil and gas and deep geothermal sectors to reduce drilling, disruption, as well as cost, and optimize the system to install ground source heat pumps. Next advantage is efficient and scalable system, which means that it can provide long lifespan, heating and cooling, and integration into thermal grids across residential as well as commercial sectors. So they are cost-effective integration, so embedding heat exchanger pipes into structures. So the structures that you can see here, from energy wall to energy piles to tunnels, and also sewers, reduce upfront costs on specifically on large projects. And the next one is thermal energy storage. So the ground acts as a natural thermal energy battery, improving reliability and reducing stress on surface infrastructure. And sustainable and renewable, which is very obvious, is natural restored ecosystem-based solution, which supports the UK's decarbonisation and energy efficiency goals, as well as importing gas can be reduced. So, and finally is their economic and environmental benefits. So ground source heat pumps specifically can save thousands of pounds in heating as well as in cooling costs, and can support cutting CO2 emissions up to around 11,000 kilograms per year. So there are lots of advantages and around this technology, but why we are not using this in the UK a lot, so it will be addressed shortly. They can deliver low zero carbon heating and cooling to building in one of the following methods. Firstly, by direct connection to a ground source heat pumps in an overlying or adjacent buildings, or by connecting to heating and cooling network either through central heat pump, which feeds a high temperature network, or through ambient loop network, which requires individual buildings to operate their own smaller heat pump. A recent study by EPSRC led by University of Leeds highlighted the contribution which buried infrastructure and underground structures, basically converted to energy geostructure, can make decarbonizing heating and cooling in the UK, which again shows huge potential that we have in the UK. And another research, again led by Leeds, EPSRC, shows that these technology geostructures, energy geostructures, can contribute in excess more than 50 terawatt hour per year of thermal energy, which can help decarbonizing heating and cooling in the UK. So in this picture, I put more detailed picture of energy piles, geoenergy piles. So you can see for this building, the piles which is designed to support the building as a structure has been used as energy geostructure. So by just embedding pipes, you can see the detailed piles. It has one U-shape pipes, one inlet, one outlet, just getting energy from the ground and use it as air conditioner heating and cooling of the buildings. That's the procedure that we use in civil engineering, basically design to get energy from the ground. That's another example of geostructure. So, uptake barriers. We talk about lots of advantages, and they were just some of them. And there has been several UK government support programs to businesses as well as to individuals to support uptaking these technology. However, there is very uptaking these technologies is very slow compared with much of European countries, and you will be surprised if I say the uptaking of this technology in the UK accounts for less than 1% of renewable energies in the UK, based on the data I collected in September 23, which I can say is nothing, 1%, despite of huge potential that we have. Recently, Crossrail for Elizabeth, I think, underground station and line, they embedded energy pipes, I can say, in their tunnels. So their tunnels is empowered with pipes to produce energy, and their tunnels are considered as geostructures, energy geostructures. So generally, challenges associated with ground source heat pumps, including geostructures, and particularly those which are relevant to the UK, can be divided into the categories which I listed below. So financial and economic challenges, policy and regulations, which is huge things to be discussed. It needs separate presentation itself. Awareness, knowledge, and social acceptance. And the next one is sustainability, environmental and geographical considerations, and knowledge and data. Technical and infrastructure challenges, which is the one that I am focusing on, technical part. What we can do is research and development. So I forget to say that this cross section, uh, right hand side, the bottom picture shows the cross-rail line and how they embed pipes into the lining of the tunnel to get energy from the ground. So, financial and economical challenges. So, firstly is high initial installation cost. So, which is mainly relevant to ground source heat pumps, meaning that they require significant upfront investment, and combined with limited, accessible, and attractive financing options for both homeowners and businesses who are developing the homes, and so affected the uptake of these systems. Another thing is market uncertainty challenges for their adoption, ground source heat pumps in general. The energy efficiency of ground source heat pumps is affected by electricity prices, but fluctuations in oil and gas markets makes predicting their price very difficult, and reducing the market certainty needed for wider adoption and confidence, basically, in taking this technology into the market and make it widely acceptable by public as well as asset owners, businesses, etc. So, policy and regulations. Policy and regulatory environment in the UK has several challenges to uptake and adopt this technology, basically, and mainly it's because of the complexity and variability of planning as well as approval processes, and it is coupled with a lack of scientific specific so let's say rewards or benefits. If you uptake this technology, okay, you have some rewards, and basically there is not consistent support to uptake this technology, and there are lots of bureaucratic hassles, and the building regulations are so strict and very, very challenging to change or accept things, especially in urban and environmentally sensitive areas. And so this has affect taking this technology in the market. And also another things is larger scale energy geostructures or energy geostructures attached to national or regional infrastructure projects face greater barriers and hassles, let's say, to be taken, to be adopted. And this is because the heat user is not necessarily the same organization that the heat producer or heat owner and energy geostructure developer. So in such cases, the energy geostructures will require connection to a network which needs further investigation and regulations. So if you use, for example, for your own property, things are easier. But if it doesn't belong to you, or you produce it from national infrastructure such as sewer pipes or the tunnels or other sort of things, so we don't have clear regulations, and it should be stored somewhere and then connected to energy network. So awareness and social acceptance is another problem. So you will be surprised if I say research published in 2020 showed that more than 60% of public haven't heard about ground source heat pumps, including energy use structures, which is very surprising. There is a significant knowledge gap for this technology, and they are not aware of the level of disruption and the long-term benefits of this technology. And it is less and less understood by general population compared to other renewable energy sources, such as solar panels for, let's say, commercial as well as residential buildings. And this is one of the reasons. The lack of awareness has led to misconceptions and lack of confidence in this technology and its contribution to sustainability. So all of them affected its social acceptance. So I can say there is a pressing need to better support the merits of this technology as a choice for low carbon energy supply for both heating and cooling. And when we compare to other less dispatchable renewable energy sources like solar, wind, air source heat pumps, so it has huge potential for financial savings and life cycle benefits. And if we cover some technical aspects or investigate further, so if we can also increase their efficiency in producing renewable energy. Okay, so environmental, geographical, and sustainability considerations. Environmental concern always exists, so around both installation process and potential impact of open loop ground source heat pumps. It doesn't apply to geostructures. It applies to ground source heat pumps because energy geostructures are closed loop, shallow geothermal energy. So it means that they don't actively interact with groundwater because they are embedded inside geostructure. For example, of energy piles or tunnels, they are embedded in concrete. The risk of pollution due to heat transfer fluid leakage is exceptionally low. It's near to zero, because of the high durability pipe materials that we use to inject water as a working fluid is water mainly. Energy geostructure can change the temperature of the ground subsurface environment. In extreme cases, it can be considered as a pollution, but well-designed individual system should normally operate at relatively low temperatures, and so it will cause very little concerns. And also lots of research has to be done to optimize the system, minimize all the risk, not only geographical or environmental concerns, also enhancing their efficiency. And in future, with significant shift that we expect to access shallow geothermal energy, there is a potential for high densities of system. So within urban areas and urban environments, which lead to higher temperature due to adjacent system interactions. And it is important to plan for this now to ensure our future is sustainable in terms of producing energy using this technology. So finally is about hydrological condition, which can affect the efficiency of the system if it's not properly assessed and designed, and thermal interactions between a pipe, infrastructure, geostructure, as well as ground under cyclic loadings of thermal condition, and all the parameters must be considered to increase the efficiency of the system. So I don't know the time, Durga. Do I have enough time? Am I behind?
Maybe if you would like to wrap up quickly.
All right then.
Thank you.
So my interest is covering technical and infrastructure challenges. So installing ground source heat pumps in both new and existing buildings is complex, I mentioned earlier, and required always modification to structure and careful navigation of subsurface infrastructure. So basically investigating the ground condition. So underground component face durability challenges. The durability and integrity and resilience of underground components, such as concrete, for example, for piles or tunnels. So they pose uncertainties, as repairing their failure is problematic and very costly. So a solution is novel approaches to backfilling grouts, and subsurface component is challenging in problematic condition. For example, in ground conditions which the soil are problematic and they are sensitive to shrinking, swelling, creeping, displaced grounds. And also impact of groundwater must be considered, so complex soil chemistry, all of these things must be considered. The thing that needs further attention, I believe, is long-term performance of the system. So under cyclic thermomechanical loading, for example, it needs further investment, as well as further understanding, if we embed the pipes inside the geostructure, how they will perform in 50 years or lifespan of the structure. So maintenance demands and shortage of skilled technicians. For example, the heat pumps and other technologies need regular maintenance to ensure optimum performance, and we have lack of technicians in this field. So this is the things that we need to train more people on this. So research and development, what we can do. So to bridge knowledge gap and enhance their efficiency, we require comprehensive research approach and creating precise site investigation, optimizing the design of the system for local condition. So ground is different from the place that I am presenting to where you are listening to me and watching me. So so we have to be careful to have detailed ground conditions, and innovations in material science can lead to eco-friendly, durable heat exchangers, both with concrete, with pipes, backfill materials, and also it can cut the installation costs and increase equipment lifespan, or the service life of the energy geostructures. And with advancement in monitoring systems, such as the advancement over 20-30 years that we have in fiber optic sensing technology to monitor geostructures as well as structures, and embracing low-cost both hardware and software computing systems, and the use of digital twins, so we can maximize the system performance, and we can facilitate the integration of this technology as one of the renewable sources of energy in the UK. So economic uptake can be supported by innovative financing models and incentive scheme based on full value assessment for society, economy, and basically whole life cycle assessment of this technology needed to be done. So, my current research on energy geostructure. So before moving on and explain the project, I would like to talk about national buried infrastructure facilities that we have at the University of Birmingham, NBIF. We are a part of the government investment for the UK Collaboratorium for Research and Infrastructure Cities, so EPSRC. University of Birmingham is part of EPSRC, and constructed as a part of that. We received 22 millions and received another 6 millions from the university. So we have national buried infrastructure facilities based on that. So it is one of its kind and facilities spanning research, innovation, education, CPDs, and training in buried infrastructure, ground, so soil structure interaction, and anything embedded into the ground in large-scale controlled environment. So the research that we are focusing is buried infrastructure and ground interactions, which is highly important for energy geostructures, either tunnels or piles, walls, anything embedded into the ground, so we can model it in a controlled large-scale environment, which none exists around the globe. Soil stabilization improvement, geophysical sensing technology, so etc. So using the facilities supports us to do lots of research in this field. So we have a pit, right-hand side on top. It is 25 meter by 10 meter. And importantly, 5 meter deep, which allows to do to model lots of underground infrastructure. So, and the middle one, we have centrifuge. Again, so if we don't want to do in our large scale facility, so we can replicate and model the reality in very small scale by using centrifuge to replicate real ground condition. And we have movable floor with lots of actuators, around 50 actuators, allows to simulate the ground movement. So, and using facilities that we have, I have a project improving heating and cooling efficiency and system resilience of shallow energy piles. So the purpose is developing a digital twin of the system. So based on the data, firstly, that we are getting from numerical simulations, it's a comprehensive numerical simulation considering all contributing parameters, thermo-hydromechanical interactions of the system, and then integrating physical experiments with computational modeling. So we want to simulate heat transfer, fluid flow, soil pile interactions. So, and then we develop a digital twin of the system. So, and feeding the digital twin with real-time data, so we can optimize the heating and cooling performance of energy pile systems. So, we have done some of these projects, so hopefully next few months I can share further details with you. So we finished numerical simulations part, and so by getting support from Reef-UKC, so we are just about to start to look into the cooling potential of energy piles, to see how we can improve the efficiency of the system to produce cooling, to be used as a cooling tool for a building. So this is the setup that we have.
Moura, sorry to interrupt. We short of time. If you like to quickly wrap
that's
up.
all. That's all.
Apologies. Brilliant. Thank you.
That's the last slide. And hopefully in near future, I can share our final data of what we have done, what we have got as a conclusion to improve the efficiency of the system. And thank you so much. So if you have any question, I'm happy to answer you. And also, if you have any technical questions about the performance of the geostructures with the ground interaction relevant to geotechnical engineering, drop me an email. Happy to support you.
Thank you, Moura. Thank you, Moura, for amazing presentation. We have few questions which we'll pick up after the end of the presentation. Yeah. I would now like to invite Florain Schabus from Barocal. Florain, are you able to hear me okay?
Yes, I can hear you well. Can you hear me
okay?
Great.
I can hear you okay. If you'd like to put up your presentation. So Florain is the Chief Commercial Officer at Barocal, a startup developing breakthrough solid refrigerant technologies. He has a background in climate, tech investment, and startup growth. He was an investor at early stage venture funds, worked for a number of years in early stage startups. And the title of his presentation is Challenges and Opportunities of Solid Refrigerant Technologies. Over to you, Florain. I am not able to see if you're presenting. Thank you.
Can you not see my screen yet?
Wait. I can't see your screen yet.
Okay, let me try again. Does this work now?
Not yet.
I've had some challenges with Teams all day, but hopefully.
Yeah, technology sometimes.
Yeah, it's really crashing. Let me try again. Can you see it now?
Nope.
Wait, give me a second. It shows me that I'm sharing my screen, but somehow it doesn't seem to work. Does it work now?
Let's wait. I don't know yet. I can't see anything appearing on the screen yet.
Wait, sorry for that. Does this work?
Yes, there we go.
Okay, great. Sorry for that. I guess, yeah, very good to meet you all, and thanks for inviting me, Durga. I will try to provide a bit of an industry perspective on some of the challenges and opportunities of introducing novel cooling and heating technologies. And as a bit of background, we're a spin-out from the University of Cambridge, have done a lot of academic work into different types of solid materials that can be used to replace conventional refrigerant gases. And since about a year's time or so, have built up a team now on the startup side to commercialize that innovation. So we'll use the next couple of minutes to tell you a bit about the journey, what we're doing, and yeah, what sort of the challenges are for startups and technology developers in that field. Maybe a bit for background. I mean, I think I'll skim over that very quickly. I mean, cooling and heating is obviously a big sustainability problem, and with rising temperatures, but also electrification, it's going to get even worse. And we're seeing that the global demand for cooling and heating is actually projected to grow by a factor of 3 to 4, both because of increased demand for cooling, but for comfort reasons, but also things like data centers, etc., which means that in a lot of countries, cooling will account for more than 40% of peak load energy demand, and certainly also in the UK with rising temperatures, the demand for cooling is growing a lot, and at the same time, of course, for sustainability reasons, we're trying to promote the use of heat pumps, right? The problem that we're trying to tackle at the company is that conventional cooling technologies most of them at least are based on vapor compression. And the problem with conventional vapor compression cycles is that on the one hand, the energy efficiency is still very low compared to what's theoretically possible. So we run very inefficient cycles. And on the other hand, even though there's a lot of regulation, we're still using a lot of refrigerant gases with very high global warming potential. Trying to shift away from these high GWP gases means that we're adopting alternatives that are more difficult to handle because they're flammable, explosive, or and that sort of limits adoption of natural refrigerants. And so the background to what we're doing at the company is really a lot of academic work into different types of solid materials that could be used as a replacement for these conventional refrigerant gases. And so traditionally, there have been, let's say, 4 major types of solid materials, so-called caloric materials, that basically change their temperature as a function of a change in field. So whether that's a magnetic field or in our case applied pressure. So there's different alternatives. And so we've basically at the university done a lot of research into all of these different fields. Certainly magnetocalorics and elastocalorics have been around for a very long time, but they had never really performed well for commercial applications. Scientifically, they have been very interesting, but and so hence there's been a lot of academic publications, but they always struggled to get real traction on the commercial side because the performance wasn't good enough of the materials, and so any systems that you built didn't have the required temperature spans, were not efficient enough, and were also based on materials that were a little bit too expensive. And so the starting point for our company has really been, okay, can we find a solid material that can compete with a conventional gas? And vapor compression is a fantastic technology, and so it's going to be very difficult to find something which can match the performance of a typical gas. In the end, though, we for the first time had discovered a solid material which undergoes or which delivers the same thermal performance as a conventional refrigerant gas, and that was by 2 orders of a magnitude bigger than any other solid before. And so, based on that sort of scientific discovery here at the university, we started spinning off the company to commercialize these novel materials. What are the advantages and why is that interesting? On the one hand, obviously, we then can have a refrigerant which has no global warming potential. So there's no leakage issues and no emissions, no fugitive emissions from the leakage of that gas. But on the other hand, we can also build systems which are a lot more energy efficient than a typical vapor compression system, because we can overcome some of the limiting factors when it comes to efficiency in a typical vapor compression cycle. And so based on these solid materials, can basically build systems which are a lot more sustainable and a lot cheaper to run from an OpEx perspective. I'd say the challenge for us has been to translate that material science innovation and that academic work into actual systems and real products that can deliver that performance, because our ambition has always been to build something which can have large-scale impact. And so it was very important for us to not stop at the academic work, but really show that this can be applied in the real world. And so we've built a number of prototypes. The one you can see here on the big picture is our old prototype, what we call the Generation 2 prototype, which has been the first ever solid system, actually, which delivers the same energy efficiency or coefficient of performance as a typical vapor compression system, which has been a nice breakthrough for us and really the starting point of the systems engineering that we have been doing. And really what we're working on now is building a very universal compressor, which basically works on our materials and can replace refrigerant gases across a large number of different applications. And the challenges for us have been, how do you design the heat transfer for such a system where you basically have a solid stationary in the system that's and that's basically being pressurized or compressed, changes its temperature in a very cyclical way, right? So you can't pump it around like in a typical system. So we need a secondary heat transfer fluid to basically extract that heat out of the system efficiently. We also had to work on the design to make it very modular and compact, because compressor had 100 years of development, so they're very small and can fit into lots of different footprints, and also making sure that in the end, the system that we built is very easily integratable with standard systems on the market. So basing it on existing supply chains, standard components, and making sure it interfaces very, very, very easily with whatever application we're targeting. And so that's what we've been working on. Built the system very much on off-the-shelf components. So there's certain hydraulics components in our system that pressurize the material. The material is sort of our secret sauce, and then we have heat exchangers to reject the heat. So in the end, very simple system. Where we are now is that this year we're building or finalizing the work on the third generation prototype, which is the first prototype that we're actually going to pilot in the field. So we're working together with existing manufacturers and producers of systems, because as a startup, it's very hard to produce something at scale, but that is necessary to bring down the cost, because of course we're producing more air conditioners than cars every year. And so in order to get costs down, give me 1 second. Sorry for that. And so, working a lot with partners to cost down the system and making sure that, we can not only deliver high performance, but also have a system which can fundamentally be manufactured at low cost at scale. So this has been always the objective. I think with now systems that are far outperforming any other systems based on solid materials, which has been quite nice that we were able to translate this academic breakthrough into actual prototypes and systems, and show that this is finally an innovation that can make it into real market applications, because we have that long academic legacy of about 15 years of research at the university. There's a number of patents underlying what we're doing, which for us as a startup is very important, because we want to make sure that we have enough defensibility and protection in the market, that we can really commercialize this innovation properly. In the end, where we see this going is really as a very universal replacement for typical compressor units across a lot of different applications, really delivering a 0 GWP solution with a lot higher energy efficiency, whether that's in cooling, heating, or refrigeration. So a lot of different opportunities for us, and something that from our perspective can have a real impact from a CO2 perspective. Because obviously we're reducing the effect of the refrigerant itself, but also through the higher energy efficiency can really reduce the indirect emissions and the energy use of the systems, and addressing probably one of the biggest impact opportunities there are globally, really. And so this is what motivates us. We're a small team. We're 8 people in the company now. Got about 4 million in funding so far as a mix of grant and equity. The university has been very supportive in that, so we still work very closely with them. And very excited to connect with anyone interested in learning more about solid state cooling and finding out if there's any potential synergies with other projects going on, whether that's in heating, cooling, or certain subsystems, heat exchanger designs, etc. Very, very open for any potential collaborations with other research groups. And I would say given that we're a bit over time, I think I would stop there. But hope this was useful, and let's definitely connect afterwards if anyone has any questions. And obviously also very happy to help if anyone has questions about the spin-out process and starting a startup in general.
Thank you, Florain, for keeping this very crisp and short and amazing presentation. I am sure there will be many people who would like to connect with all the presenters. I would now like to request all the presenters, Ahmed, Moura, and Florain, to turn on the cameras if possible, so we can take a couple of questions. And the first question I think that's the only question we have received so far from Joel Hamilton, and I think it's for Moura. I don't know, Moura, if you can see the question. It says, which of these do you think have the biggest impact on uptake of energy geostructures? Lack of regulatory requirement, lack of expertise, disconnect between construction priorities and user priorities, competing technologies, waste heat, etc. And his further question is, what are your thoughts on balancing heat drawn from ground with heat injectors as is required in some countries?
That's a very good question, but very difficult to prioritize, basically. The biggest impact. Maybe lack of number 1 and 2. So I can see, I'm a technical person. I'm looking into the problem, looking into technical part of the problem, looking into ground and geostructures and their interactions. So obviously I would say lack of expertise, technical expertise, and lack of data to convince, lack of technical data, in my point of view, lack of technical data to convince industry in general, asset owners, builders, and then government to uptake this technology. So the thing is, we also in EU and other countries, they are using this technology, but I think their long-term performance is not clear. So we don't have lots of data to show the people who are contributing in making decisions to convince them to uptake this technology further. So biggest one. So if I don't consider my expertise, lack of regulations. We don't have regulations in the UK. In Germany, Switzerland, they do have some regulations to uptake this, and they're doing quite well, which is linked to question number 1 as well. But I think we need regulations. For regulations, I can say we need closely, as academic person, closely, we need to work with industry to make this happen. So, and not just industry, to uptake this with different people through the supply chain. So policymakers, asset owners, decision makers, industry, so those who are involved in building industry, in underground assets, so everyone. But lack of regulations, and I know public awareness hasn't been one of the options, but I think public awareness is important. Publics are, I think, aware of, for example, solar panels for their own individual properties, but they don't know much about this potential, that we have huge potential in the UK. So not only for geostructure, so for shallow geothermal as ground source heat pumps. Easily they can install it. So Joel, right. I hope I answer your question. I wasn't sure to pick up one of these. It's very difficult for me, but maybe number 1 and 2.
Thank you, Moura, on this explanation. I hope if he has any further questions.
I think there was another question which I tried to type the answer. So if you want, you can go through the question.
Yeah, sure. What are your thoughts on balancing the heat drawn from the ground with heat injected as is required in some countries?
It is very, very good question. So firstly, one of the things that we are trying to answer via the research that we are doing at here, University of Birmingham, is optimizing the system. One of the parameters that we are looking into is seeing basically the balancing the system, basically how much energy we can extract without impacting the ground heat, giving enough recovery time to the ground, for example, as one solution. Another solution is installing ground source heat pump, injecting water to help the ground for recovery time. So in ideal world, a government, for example, needs to regulate this. So to manage the balance. So there are areas in London, I know, and elsewhere, which I can't remember where, which this happened, and there was lack of balance. And this lack of balance has impacted the other buried assets and also the ground energy as well. So the temperature of the ground, basically. As far as I know, currently there is no formal regulation, instruction, which definitely will cause issues. So, and specifically considering climate change and that the demand for cooling will go up and up in future, this may become a very critical and very urgent issue, which needs to be addressed, I believe. I know I mentioned earlier in the first question, so I know some countries, for example, Switzerland and Germany, they do have regulations, and so to for the thermal balance, to avoid long-term degradation of the ground's thermal capacity, which I say ground needs recovery time. We can provide recovery time by other technologies as well. Needs investigation, needs further research to be done to have that regulations, considering the ground condition that we have here in the UK. And also weather condition in the UK is totally different. So the demands, for example, that we need cooling system is totally different to the one that we may have in another country. So every country should consider their own conditions, ground condition, hydrological condition, environmental condition, and demand.
Thank you, Moura.
So, no worries.
Very well explained. And we do not have any further questions. Ahmed, if I'm sure there will be many attendees who would be very interested in understanding how Reef-UKC is researching in this area and how we can make a difference in the sustainable cooling sector. Would you like anything? Would you like to add anything? We have a few minutes if you want to add anything.
Not really. So what we encourage here actually engagement from everyone, and as I said, just you need to participate, and we cover all the cost. If you have really nice idea, so we can support your idea, giving you some seed fund, and this should lead to a bigger project. So we aim to do more of these activities. So stay tuned, and you'll get alert actually for the new events.
Thank you, Ahmed. We have another question from Armin. It's a technical question. In magnetocaloric refrigeration, regeneration is typically used to increase the effective temperature span. Is there a similar concept or technique applied in barocaloric cooling to extend the temperature span?
I think it's for Florain. So
yeah, I was hoping it's for Florain. I think he had some technical issues, so I think we have lost him. Armin, I'll try and get this question answered from Florain. Apologies for this for now. So once again, I think I would like to thank you all our presenters, Ahmed, Moura, and Florain, for their great presentations today. And I would also like to thank you to all our attendees who joined us in this webinar. And as Ahmed mentioned, there will be few events and activities coming up. So stay tuned on the website and LinkedIn news. Please do follow the Reef-UKC on LinkedIn so that you can stay updated. Yeah, once again, thank you, everyone, and have a great day. Thank you, Moura. Thank you, Ahmed.
You too. Thank you.
Thank you.